In this section, we're going to look at conic sections, and specifically, we'll deal with conic sections that have been shifted. Either the center has been shifted from the origin or the vertex has been shifted from the origin. So we've been looking at conic sections. We have circles, ellipses, parabolas, and hyperbolas. We saw how each of those came from the intersection of a three-dimensional cone with a plane. Now we're going to transform the conic sections by shifting the center or shifting the vertex left and right, and then up and down. If I want to shift h units in the x direction, then in each of the formulas I've seen, all I have to do is replace the x value with the quantity x minus h. If h is positive, it will shift my object, in this case my conic section, to the right. If h is negative, it will shift the conic section to the left. We can also shift in the y direction by replacing each y value with y minus k. And again, if we have a positive k, it will shift the whole conic section up. If we have a negative k, it'll shift the conic section down. So, for instance, if we have a circle centered at the origin, we've seen that the equation for that in standard form is x squared plus y squared equals r squared. If I want to center that at the point h comma k, I just replace the x with an x minus h, replace the y with a y minus k, and I'm all set. So the circle centered at the point h comma k with radius r is x minus h quantity squared plus quantity y minus k quantity squared is equal to r squared. Now, we still have the basic circle information that we had from before. R is the radius of the circle. The diameter is twice the radius. But now we're just centering it at a different spot. That's going to be very similar with ellipses. We saw that one of the equations for the ellipse look like this. We could also replace the a squared and the b squared. We could swap those, but let's just take it one example of an equation of an ellipse. X squared over a squared plus y squared over b squared equals 1. Well, if I wanted to center that at hk, I just replace the x with an x minus h, replace the y with a y minus k, and then all we've done is shift that ellipse h units in the x direction and k units in the y direction. The information on the ellipse is still basically the same, just shifted over. So our major axis has length 2a still. The vertices are still going to be on the ellipse at the end of the major axis. The minor axis is going to have length 2b. Co-vertices on the ellipse are at the end of the minor axes. And the foci are going to be along the major axis, c units from the center. And the c calculation for an ellipse is c squared equals a squared minus b squared. The eccentricity is still c over a. In the same way, here's one example of a hyperbola. X squared over a squared minus y squared over b squared is equal to 1. If we replace the x with an x minus h and the y with a y minus k, then we get the hyperbola centered at hk instead of a hyperbola centered at the origin. Again, this is just one version of the hyperbola. You could do this with the other equation of the hyperbola as well. But again, the same information will be there. Transverse axis is length 2a. Vertices are at the end of the transverse axis. Conjugate axis is length 2b. Asymptotes will have slope either plus or minus b over a or plus or minus a over b, depending on which version of the hyperbola I have. And then the foci are going to be along the transverse axis, c units from the center. And with the hyperbola, c squared is equal to a squared plus b squared. Eccentricity is still c over a. Again, all of these things were consistent with what we had when we looked at hyperbolas centered at the origin. Lastly, we could also deal with parabolas. A parabola whose vertex is at the origin could look like y squared equals 4 times p times x. It could also look like the other version, which was x squared equals 4 times p times y. But if we want the vertex to shift to the point hk, we would get y minus k squared is equal to 4p times x minus h. And we could do a similar shift with the other parabola formula. But once again, focus is going to be still p units from the vertex, whichever formula that I have. Directrix line is going to be p units from the vertex in the opposite direction as the focus. So basically, all we do is we look at every feature of the conic section and we've just shifted them horizontally and vertically appropriately. So let's take a look at these two examples. Find the center of the ellipse, find the center of the hyperbola. Go ahead and push pause. This should only take a second or two. And then in a couple of seconds, I'll show you how it's done. So hopefully we can see, again, this comes pretty easily. Hopefully you can see that. The center for this ellipse, which is x minus 2 quantity squared over 25 plus y plus 3 quantity squared over 121 is equal to 1. The center is going to be at the point 2 comma negative 3. Be careful about that. It's x minus h and and y minus k. So y plus 3 is a negative 3 as your k. For the center of this hyperbola, well, the center is going to be at the point negative 1 comma positive 7. Again, look at where x is. It's x plus 1, so we have a negative 1 as our x, and center for the x, and y minus 7, so we have a positive 7. You can always ask yourself, like, what makes the terms equal to 0? And plug in that number. So center for this ellipse is 2, negative 3. Center for this hyperbola is negative 1, 7. Let's go ahead and do another couple of examples. Here we'll find the center of a circle and the vertex of a parabola. Push pause on the video, try this on your own. In a couple of seconds, I will write the answers down. All right, for the circle, we have x plus 9. So the x value of the center of the circle is going to be a negative 9. And we have y plus 11. So the y value for the center of the circle is negative 11. So the center of that circle is negative 9 comma negative 11. If I want to find the vertex of this parabola, the center is going to be at the point x value, which is 6, y value, which is -3. So that's the point 6, comma, -3. So now we've found the center of the circle. We found the vertex of the parabola. And obviously earlier we found the center of the hyperbola, the center of this ellipse. Now, speaking of that ellipse, that'll give us a good idea of how to find features of the ellipse. Since we did this in cases where the center of the ellipse was at the origin, and we've done the same thing where the center of the circle is at the origin and the center of the hyperbola is at the origin and the vertex of the parabola is at the origin. Since we've done all of those, we'll just do one example where we find the features where the origin is not the center or the vertex. So we'll just find the features of this ellipse. Go ahead and push pause on the video if you'd like to do that on your own. Otherwise, I will do it in a couple of seconds. You can look back and figure out what the features of the ellipse are. I'm not going to do that right now because we've done this so many times. Notice that here, if it were just x squared over 25 plus y squared over 25, we'd start out by finding which, if the ellipse was stretched out more in the x direction or the y direction. So which direction is the ellipse stretched out more in? It's stretched out more in the y direction because the bigger number, the bigger denominator, is underneath the y squared component. So a squared is going to be the 121. That means a is going to be 11. And b squared is equal to 25. That means b is equal to 5. So this means that the vertices are going to be 11 units away from the center in the y direction. So the two vertices are going to be 2 comma, then we're going to have -3 plus 11. So we're going to move 11 units up for hitting one vertex. And the other vertex is going to be -3 minus 11 as the y value. Is going to have -3 minus 11 as its y value. Now I'm going to do the arithmetic here. -3 plus 11 is 8. -3 minus 11 is a -14. Oh, hit the wrong button. Since A is 11, the length of the major axis is 22, twice 11. Now the covertices, to hit those, we're going to move in the x direction from the center. So what we're going to do is we're going to start at 2, -3, and then we're going to add 5 units to the x value. And then we're going to take 2, -3 and subtract 5 units from the x value. That'll get me to my covertices. And again, just using the algebra, 2 plus 5 is 7. 2 minus 5 is a -3. So my two covertices, we move in the x direction because the smaller number was underneath the x squared part. And we move 5 units since b was 5. That means the length of the minor axis is 10. To be able to get the foci and the distance between the two foci and the eccentricity, I have to calculate c. And remember, for an ellipse, c squared is a squared minus b squared. In this case, that means c squared is 121 minus 25. If I take 121 and subtract 25, I get a 96. So C is the square root of 96. By the way, that's going to be 4 root 6 if I simplify. I won't simplify, but that's how it is. Now, remember, the foci are along the major axis. The major axis is in the y direction. And again, the reason I know that is because I know it's stretched out more in the y direction than the x direction. So the foci are going to be along the major axis. And then we take a certain distance from the center. Our center is at 2, -3 in both directions. So we'll move up and down square root of 96. So here's what we do for the foci. The first focus is going to be at 2, -3 plus the square root of 96. And the second focus is going to be at 2, -3 minus the square root of 96. Obviously, each of those y values can be transformed into an approximate decimal if we'd like, but those two y values will be irrational numbers. And just like we've done before, the distance between the two foci is going to be 2 times c. That's 2 times the square root of 96. And the eccentricity is going to be the fraction square root of 96 divided by 11. And if I type that into my calculator, square root of 96 divided by 11 becomes about 0.89. So as you can see, to find the features on an ellipse, all we're really doing is we're doing the same process that we used when we started where our center was at the origin, except now our center is not at the origin, so everything gets shifted by that amount. Instead of moving up 11 units and down 11 units to get to our vertices from the origin, now we're moving up and down 11 units from the center. Instead of moving left and right 5 units to get our co-vertices from the origin, now we move left and right 5 units from the new center. Same thing with foci, we're moving up and down square root of 96. So that's how we can deal with finding the features of an ellipse whose center is not the origin. We could have done a similar thing for any of these conic sections. We did that for the ellipse. We could have found the same types of features for the hyperbolas that we did before, and now just shifting it 7 units down, 1 unit to the right. Or, excuse me, 1 unit to the left. 7 units up, 1 unit to the left, excuse me. So shifting the center of our hyperbola. Or now shifting the center of the circle 9 units to the left, 11 units down. Or shifting this parabola, or excuse me, doing the same, finding the features of the parabola, and now we just shift 6 units in the x direction, -3 units in the y direction. So that's if we have our standard conic sections and our standard formula. But what if the conic section is not in one of those standard formulas? We're going to ask two things. First off, we're going to find out how to identify it, and then we'll convert it to a standard form. Now, in general, when I'm talking about non-standard conics, we should realize that any conic section can be written like this one. Any of our non-standard conic sections can be rewritten like this, where we have x squared terms, y squared terms. XY terms won't come into play in this class, but in other classes, if you wanted to shift and skew them, you might get an XY term. An X term, a Y term, and a constant term set equal to 0. So we have x squared and y squared terms. One of those could have coefficient of 0. So the A, B, C, D, E, and F are just real numbers. So any conic section can be written this way. And obviously, when we have the nice standard form, our conic sections are written this way. Now, the key to identifying conics, if they're written in this form or something like it, is to focus on the squared terms. Notice that the circle here has x minus h quantity squared. When I square that, I'll get x squared plus some other terms involving x and a constant. When I square this, I'll end up with y squared plus some other terms involving y and a constant. But the point is, when I have this multiplied out, I'll get an x squared term and a y squared term, and both will have coefficients of 1. Now, we can manipulate this equation in lots of different ways. We could add terms to both sides. We could subtract terms from both sides. We could multiply both sides by a constant number. But no matter what I do to this equation, the x squared term and the y squared term written on the same side will have the same coefficients. Think about that. If you multiply by a constant number on both sides, x squared and y squared have the same coefficients. If I subtract or add a term to both sides, again, x squared, y squared, if they're written on the same side, have the same coefficients. That's going to be different with an ellipse. Think about this. If I square this, I square this x squared is going to have a coefficient which is like 1 over a squared. This y squared will have a coefficient that's 1 over b squared. Now they're both going to be positive when I square them out initially. One of them is going to have a positive coefficient of a squared, 1 over a squared. The other is going to have a positive coefficient of 1 over b squared. If I could multiply both sides of the equation by a number. That won't change the fact that the coefficients will be different, not the same number. However, when I write the x squared term and the y squared term on both on the same side, I will get either both coefficients being positive, or if I'd have multiplied this equation by a negative on both sides, then both coefficients will be negative. So I'll either have both coefficients on the x squared and y squared as positive, or both coefficients on the x squared and y squared as negative. That's going to be the opposite with the hyperbola. Notice that the x squared term will have coefficient 1 over a squared. The y squared term will have coefficient negative 1 over b squared. So one's going to be positive, one's going to be negative. If I multiply the equation by both, on both sides by a -1, then I'll just change which one's positive and negative. So if x squared and y squared on the same side, they're going to have one positive coefficient and one negative coefficient. And the parabola is probably the easiest one to identify because with the parabola, we'll have a y squared term. If I have this form, we'll have a y squared term, but no x squared term. If I have the other version of the parabola, I'll have an x squared term, but not a y squared term. So in short, this is how I identify conic sections by their coefficients. I focus on the x squared and the y squared term when written on the same side of the equation. If the coefficients on the x squared and y squared terms are identical and on the same side of the equation, I know I have a circle. If the coefficients of x squared and y squared are both positive or both negative when x squared and y squared on the same side of the equation, then I have an ellipse. If I have coefficients where one is a positive and the other is a negative, again, written on the same side of the equation, then I have a hyperbola. And if one coefficient on the x squared or the y squared is 0, so in other words, I don't see an x squared term or I don't see a y squared term, then I have a parabola. So this is an easy way to identify conics just by looking at the coefficients of the x squared terms and the y squared terms. So let's do that. I'll go ahead and do this. If you want to try this on your own, push pause on the video. In a couple of seconds, I will show you how this one is done. This identification can go pretty quickly once I know what's going on. So for instance, in this first one, we have an x squared and a y squared on the same side. The coefficient on the x squared is a +1. The coefficient on the y squared is a +4. So they're both positive and on the same side of the equation, but they're not equal. They're not identical. One's 1, the other's 4. So that means I have an ellipse in this first equation. In the second equation, one coefficient is 4, the other is a -7. So one is +4, the other is -7. X squared and y squared are on the same side. So I have a hyperbola. In this third example, we have a y squared term, but you can see that there's no x squared term around. So that means we have a parabola. Now for this last one, this one's a little bit tricky because the x squared and the y squared terms are not on the same side of the equation. One of them is on the left side, one of them is on the right side. Right now, it's a +3 on the x squared and a 2 on the y squared. But if I were to put both on the same side of the equation by subtracting 2y squared from both sides, notice one of the coefficients would be positive, the other would be negative. So I'd end up with a hyperbola in this case. So be careful about that. We have to realize that we're talking about coefficients when those terms are put on the same side of the equation. But that last example is a hyperbola because of that. So the x squared and the y squared coefficients tell me what type of conic section it is immediately. Let's do another example like that. Again, I'll give you a chance to do this on your own. You can push pause on the video. In a couple of seconds, I'll show you how each of these is done. All right, let's go ahead and do this. This first equation, we have an x squared term. We have no y squared term visible, so the coefficient of the y squared term is an implicit 0. So we have a parabola. We have no y squared term, essentially. On the second one, here we have an x squared and a y squared on the same side of the equation, and both coefficients are 4. That means that conic section is going to be a circle. Now, there's a couple of things going on in these last two examples. First off, instead of having just an x squared, we have 3 times something with an x in it, quantity squared, specifically 3 times the quantity x minus 1 squared. Now, when we square that out, we'll get an x squared term, and we'll get some other terms as well. So I think of this as 3x squared plus some other things is equal to 6 plus, we're going to get 2y squared plus some other things. Don't worry about the other things because they're not going to involve an x squared or a y squared. I should say don't worry about it for the purpose of identification. We have a 3x squared on the left side, a 2y squared on the right-hand side. If we were to put both of them on the same side, one of them would be a positive coefficient, the other would be a negative coefficient. We'd have 3x squared minus 2y squared. Let's go ahead. Well, I won't do that. That's fine. And so this is a hyperbola. If I put the x squared and y squared terms on the same side, one would be a positive, one would be a negative coefficient. The same is true here. If I just look at the identification part, we get a 9x squared plus a bunch of other stuff is equal to 36 minus 4y squared plus some other stuff. If I were to put those on the x squared and the y squared terms on the same side, then I would get 9y squared plus 4y squared. So 9x squared plus 4y squared plus some other stuff is equal to 36 plus some other stuff. So notice that in this case, the coefficients on x and y are both positive. They're not identical, so it's not a circle, but they are both positive. So we have an ellipse there. So this allows us to identify any conic section, no matter how it's written, whether it's written out and expanded, or whether we have things with parentheses and squared, or whether it's in one of our standard forms. We should be able to easily identify what type of conic section we're looking at. Now, once I've identified what type of conic section that I'm looking at, then I can force it to be in one of these standard forms. Obviously, there's different standard forms for the ellipse and the hyperbola and the parabola. So if you want to switch the x and the y with the hyperbola, or if you want to switch the a and the b with the ellipse, or what piece is being squared in the parabola, that's fine. But we can translate any conic section into one of these four, any of the non-trivial conic sections into one of these four, and put it in this standard form. Now, there's a couple of ways to do that. We can use basic algebra to do that in some cases. But most of the cases we just got done identifying, we'd have to use completing the square to force the standard form. So let's do an example. Let's convert this into standard form. I'll show you how to do that. This is one of the ones we identified in example 4. We identified this as an ellipse, and now we're going to put that ellipse in standard form. Now, the way I would do this is I would take x squared and then I'd match it up with the minus 6x. So I'd put the minus 6x next to the x squared, and then I would leave a blank, whoops, before I put 4y squared plus 16y plus 21, okay? You could put the 4y squared plus 16y plus 21. You could subtract each of those three terms and put it on the right-hand side as well, but it's unnecessary in this case. Then I would complete the square. Now, I can do that in this case because the coefficient of x squared is a 1. So all I do is I say, in order to get x squared minus 6x, I would need to take x minus 3 and square it. If I did that, I'd get x squared minus 6x plus 9. So I need to add a 9 to both sides of this equation. And now what this equation is this perfect square plus 4y squared plus 16y. I think I'll subtract 21 from both sides as well while I'm doing this. 9 minus 21 would be a negative 12. So I'd end up with that. At this stage, now I have completed the square with the x part. Now I need to complete the square with the y part. In order to do that, I need a coefficient of 1 in front of my y squared. So I divide everything by a 4. I divide the x minus 3 squared by a 4. And then I divide the 4y squared by a 4. And then I divide the 16y by a 4. I'll leave a blank, and then I'll put equal to negative 12 divided by 4, which is a negative 3. Now I can complete the square on the y part. So let's go ahead and do that. Now, the y part, we're going to get y squared plus 4y. So what I need to square is a y plus 2. That'll give me y squared plus 4y plus 4. So I'll add a plus 4 to the left-hand side and a plus 4 to the right-hand side. So I get this, and this already is the standard form for an ellipse. We get x minus 3 squared over 4 plus y plus 2 squared, technically over 1, is equal to 1. If this number was not a 1 on the right-hand side, then I divide all the terms by that number. But there you go. That's the standard form for an ellipse. And we could find all of the features. For instance, it's easy to see that this is centered at 3, -2. The a value is going to be 2. A squared is 4. The b value is going to be 1 because b squared is 1. The major axis is going to be in the x direction. The minor axis is going to be in the y direction. And then you could find the foci. They're going to be stretched out in the x direction. So you can find all of the features of this ellipse now that I've converted it to standard form. This required me to do 2 completing the squares. And remember, when you're completing the square, you're going to do half of your coefficient of x minus half of that squared, and then I square the -3, giving me a +9. I need to get a coefficient of 1 in front of all the squared terms when I complete a square. So I do y squared plus 4y. Half of 4 is 2. Square that, you get a +4. Add that +4 to both sides. And we were all set. So this was one where we knew we were going to get an ellipse. And so we just had to force that standard form by completing the square twice. Here's another example that we've looked at. It's pretty obvious that this is a parabola. So let's convert this parabola into the standard form for a parabola. Go ahead and try this one on your own. It's a little bit easier than the last example because the last example had 2 completing the squares that we had to do. This one only has 1. Push pause on the video. In a couple of seconds, I'll show you how to do this on the screen. All right, in this case, by the way, the standard form of the parabola we're going to get is going to be y minus k quantity squared is equal to 4 times p times x minus h, because I see the squared portion on the y value. Since the y parts and the x parts are going to be on opposite side in the standard form, I'm going to force that immediately. I'll take y squared minus 8y, and then I'll leave a blank, and then I'll add 8x to both sides and add 24 to both sides as well. Now we lucked out. The coefficient on the y squared was 1, so I can go immediately into my completing the square and taking y minus 4 because -4 is half of -8. When I square -4, -4 times -4 gives me a +16. And so I can add 16 to both sides to make this equation equivalent to the one below it. So this left-hand side is y minus 4 squared, and the right-hand side is 8x plus 40. Now I need to do one more step because the right-hand side isn't quite in standard form yet. I need to factor out the coefficient of x on the right-hand side. That would give me y minus 4 quantity squared is equal to 8 times the quantity x plus 5. And now we're in standard form. And we can see that the vertex is going to be at the point -5, comma, +4. And the p-value is going to be 2. So let me just state what I'm saying there. Here we knew the parabola looked like this. That means I know, since the p is positive, that means the parabola is going to be pointing to the right. I know the vertex is going to be here. The directrix is going to be a vertical line. The focus is going to be on the inside of that parabola. So if I wanted to find the features, I would say the vertex of the parabola, now I can read that off, is -5, comma, +4. The focus, well, since P is obviously 2, 4P is 8, so P is 2, I have to move 2 units to the right. If I move 2 units to the right, the focus would be at, I'd take -5 plus 2 as my new x value, and then the y value stays at 4. So I'd get -3, comma, 4. And then the directrix is a vertical line. So that's going to be of the form x is equal to a number. And that's going to move 2 units to the left of my vertex. My vertex has x value of -5. So 2 units to the left of that is x equals -7. So take -5 minus 2 and get a -7. So once I have the standard form, getting those features is pretty straightforward. If you forgot all of the relationships between the standard form and the features, then you can look that up in previous videos. Now here's another example that we had, which we had identified earlier in example 5 as an ellipse. We had 9 times the quantity x plus 3 squared equals 36 minus 4 times the quantity y plus 1 squared. So let's convert this into standard form. In this case, the completing the squares is not necessary because I already have x plus 3 quantity squared and no other x values. And I already have y plus 1 quantity squared and no other y values. So in this case, it's kind of like we've already done the completing the square. So I don't need to complete the square here, but I do need to utilize some algebra to make this equation into standard form. Let's show how to do that. In this case, what I'd do is I'd add 4 times the quantity y plus 1 squared to both sides. If I do that on the right-hand side, that just leaves me 36 on the right-hand side. And on the left-hand side, I get 4 times the quantity y plus 1 squared, along with 9 times the quantity x plus 3 squared. So 9 times the quantity x plus 3 squared plus 4 times the quantity y plus 1 squared equals 36. Now, I forgot to mention, we identified this. This is an ellipse. You can see that easier here because we have 9x squared plus 4y squared on the same side. Those are obviously two numbers that are both positive. We want this to be equal to 1 on the right-hand side in the standard form of the ellipse. So all we would do is we would take this equation and then we divide both sides by 36, which would divide each term by 36. That would give me a 1 on the right-hand side. And then 4 divided by 36 simplifies to a 1 over 9. I'll leave off the coefficient of 1. 9 over 36 simplifies to a 4. And so that's the standard form for the ellipse. And we could say that it's centered at -3, -1. We could say that it's elongated in the y direction more so than in the x direction. We could say that A is 3 and B is 2 and get the vertices and covertices and foci and all of that other stuff based on the standard form for this ellipse. So this one was a little bit nicer in that we didn't have to complete the square because we were already had y plus 1 squared and x plus 3 squared and no other y's or x's. Now the last concept that I'm going to talk about in this section is the concept of eccentricity. Remember we said conic sections have differing eccentricity. We've seen that in the ellipse, the eccentricity is always between 0 and 1. And with the hyperbola, the eccentricity is always bigger than 1. It turns out that circles and parabolas also have eccentricities. With every circle, the eccentricity is 0. With every parabola, the eccentricity is 1. So if you look at going on ellipses and hyperbolas and circles and parabolas, eccentricity of 1 is right between the ellipse and the hyperbola. So in some way, the parabola is in between an ellipse and a hyperbola. And a circle has eccentricity of 0. It's not, and what that kind of means with a circle is it's not stretched out in the x direction more than it is in the y direction or vice versa. Now, there is a connection between the eccentricity of a conic section and the cone and the plane in 3 dimensions that make that conic section. Let's take a look at that. So here's our graph of that 3-dimensional cone and a plane intersecting that cone. Now, I'm going to take a look at how this plane cuts the cone. I want you to notice that if the plane is perfectly flat, in the XZ axis, that would mean that this plane has 0 slope. So if the plane is flat, then where the plane and the circle, where the plane and the cone intersect, we get a perfect circle. Now that circle can be bigger or smaller depending on the height of the plane. So as the plane gets higher, we get bigger circles, but it still is cutting flat. As the slope increases, as the slope of this plane increases, that circle gets elongated in one direction. and we end up with an ellipse. Notice that here I have the slope of 0.33, and that ellipse keeps getting longer and longer and longer until I hit a slope of 1. And when I hit a slope of 1, that's where I end up with the parabola. So the slope of the plane is matching the slope of this three-dimensional cone, a slope of the side of the three-dimensional cone. That's where we get a parabola. And then as that slope gets higher, then all of a sudden we end up with a hyperbola. So the eccentricity, in some sense, is telling me at what angle does this plane cut the cone. If it's 0, I get a perfect circle. Anywhere between 0 and 1, I just get an ellipse. And as I get closer and closer to 1, that ellipse gets more and more elongated. And once I hit 1, then I get sort of a infinitely elongated ellipse, which becomes a parabola. That's why this edge of the parabola and the side of an ellipse looks so similar. And then as we go over 1, then eventually we cut both sides of the cone, and I end up with a hyperbola. And again, that's why at the bend, the hyperbola looks very similar to a parabola, but at the edges, it looks similar to a straight line, or to two straight lines, I should say. At the bend, it kind of looks like a parabola, but towards the edges, it looks like a straight line. So there we go. That is how eccentricity is connected to how the plane cuts the cone. And that's kind of what eccentricity is telling us. So closer to 0, we get closer to circular. Closer to 1, we're closest to a parabola. If I have a hyperbola and it's really close to 1, then it's kind of closer to two parabolic shapes. If it's closer to infinity, then it's closer to two straight lines, less parabolic and more straight line looking. So that it's kind of easy to see that on the ellipse. The closer to 0, the closer to a circle, closer to 1, the more stretched out the ellipse is. On a hyperbola, it's a little bit harder to visualize that. So we'll go ahead and I'll try to graph a hyperbola and mess with the eccentricity so we can visualize that. So I've kind of messed around with this, and what I've done is I've graphed a circle first. That's y squared over a squared plus x squared over b squared equals 1. This circle you can think of as the same thing as an ellipse, where a and b are both the exact same number. As I start increasing my value for a, oh, I'm sorry. So notice that the eccentricity of a circle is 0. Okay, I couldn't use E for eccentricity, but I could use D. So D equals C over A. Eccentricity is 0. And then as I start increasing the value for A, as that circle gets more, or the ellipse gets more and more stretched out, you can see that the eccentricity is getting closer and closer to 1. And it doesn't take very long to actually get that far or that close to 1. So if you just stretched it out to here, then the eccentricity all of a sudden becomes 0.75 roughly. And if I stretch it out more, it gets pretty darn close to 1 pretty quickly. And as I stretch it out really, 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 really far, I can get really, really, really close to 1 for that eccentricity, 0.996 in this case. And that means, again, for the ellipse, the more you stretch it out, closer you get to 1. Now, let's deal with a hyperbola. I'll have to switch the formula for C, for finding C, but here's a hyperbola with A and B equal to 2. Pretty standard hyperbola, both A and B are the same. This eccentricity is 1.41. Notice as the eccentricity gets pretty darn big, this hyperbola starts looking like 2 straight lines almost at this curve, at the turn. As the eccentricity gets closer and closer to 1, then at this turn, they're a little bit more sharp. They're a little bit more parabolic looking at the turn. Hopefully that makes sense. Let's do this. Again, as you get larger eccentricities at the turn, these lines look straighter. Okay. So that's what's happening for eccentricity on hyperbolas. And then closer to 1, we bend faster at the turn. They look more parabolic shaped. So that's what I mean by what the eccentricity tells us. With an ellipse, the closer the eccentricity is to 0, the closer we get to circular. The closer it is to 1, the more stretched out it is. With a hyperbola, the closer to 1, the closer we look like 2 sharp turns. The closer to infinity means that the 2 turns are more straight line looking. But there you go. Now we've looked at a lot of features of conic sections. We've shifted conic sections. We've rewritten conic sections into their standard form. We've got features of those conic sections once they're in standard form. And we've investigated the eccentricity and what that tells us. So this is the end of this video on conic sections.